Hi all, this is lecture 16. This is on section 4.6 and 4.7. We're doing exponential and log derivatives here. So in addition to the trig functions that we picked up in section 4.5, we also want to add in the special functions of exponentials and logarithms. So we're going to start with e to the x. And again, we don't have any rules for this because we don't have rules for e's. We have rules when the number is in the exponent and the variable is in the base, but not vice versa. So that's what we're going to work on today. So in that case, we're going back to the limit definition of the derivative. So we want f prime of x is the limit as h goes to 0 of f of x plus h. Great. They look like they need to be brushed, Ellie. Minus f of x all over h. Sorry about that. So we want the limit here as h goes to 0 of e to the x plus h minus e to the x all over h. So what we do here, typically we're trying to figure out, do some algebra and then factor. So what we can do here is we can split that e to the x plus h. Keep in mind that if you had x squared times x cubed, you would take the x and you would add their exponents together. So I can split that up and turn that into multiplication. So if I do the reverse, if I take the x to the 2 plus, 3, that would give me x to the 5th. So if I take the x to the 2 plus 3, I can split it back up using multiplication. So that's what I can do here with my e to the x plus h. This can be e to the x times e to the h minus e to the x all over h. And now you see that I have an e to the x in each term, and I can factor that out. So I have an e to the x times e to the h minus 1, and I'm going to keep the h underneath the part that has h's. All right, with three things that are multiplied together, we can do that, right? Your parentheses go here. Okay, now the e to the x has no effect from the limit as h goes to 0, so that can come out front. So I can make it e to the x times the limit as h goes to 0 of e to the h minus 1 over h. And this, let's take a quick peek at the graph of this. So if we go to Wolfram Alpha and we graph that function, oh, sorry, don't know what just happened. Let's ask it to plot e to the x. Oh, look, it's got an example right there. E to the x minus 1 over x. And if we plot that and look at the limit as x goes to 0, right, because my x's are in my h spot, you can see it crosses right at 1. And actually, the thing here is that e is actually the number defined such that this limit is equal to 1. So that's kind of the way that it's defined. Pi is defined as the ratio of the circumference to the diameter of a circle. E is defined as the number that makes this limit right here equal to 1. And so when you take e to the x times 1, you just get e to the x. So notice, and it's way down here, that the derivative of e to the x is just e to the x. Okay, so that's what we just showed. All right, now if we have a different number to the power of x, we're going to do the same exact thing. So this is f prime of x equals the limit as h goes to 0 of 2 to the x plus h minus 2 to the x all over h. And we split it the same exact way. So 2 to the x times 2 to the h minus 2 to the x all over h. Factor out that 2 to the x. So that's 2 to the x times 2 to the h minus 1 all over h. And that 2 to the x comes out front. And this is the limit as h goes to 0 of, we don't need that, 2 to the h minus 1 all over h. Now we know this limit's not going to be 1 since we know that e is the number that makes that 1. So let's go take a look at what its graph might be. So if I go up here, I can change this to 2. Whoops. To the x minus 1. And here you can see that that is not equal to 1 anymore. But it is actually, and you can see this if I plug it in a calculator, this is actually equal to the natural log of 2. So this is 2 to the x times the natural log of 2. So for our derivative for 2 to the x, that's just 2 to the x. You get the same thing back again, and you multiply by the natural log of 2. In general, if you have any number to x, you get that same thing back again, a to the x, times the natural log of a. Okay. Note that this actually works for our e as well, right? So if you think about using this rule for the e, you'd have that the derivative of e to the x is e to the x times the natural log of e this time, but the natural log of e is just 1, so this just turns out to be e to the x. Okay, so it is consistent across all of our rules. Okay, so those are our exponentials. What about logs? Okay, so in this case, we're going to use what we know about the exponentials that we just figured out and implicit differentiation. Okay, so the first thing I'm going to do is I'm going to switch this back to y equals. And this is a little proof that you are going to need to know. So if I let y equals an ln x, then what I can do is take the e of both sides and that gives me e to the y equals e to the ln x, the e and the ln cancel, and I get a plain old x. Okay. Then I can take the derivative of this using implicit differentiation, right? Notice that my y is now buried inside the function. So the derivative of e to the y is e to the y, but we have to differentiate the y that's in there, so times dy dx. And the derivative of x is equal to 1. If you divide both sides by e to the y, this is 1 over e to the y. And so there's our derivative, except we started out with a function of x, and my derivative is in terms of y. So what I want to do is I want to replace that e to the y, but do I know what e to the y is equal to? And the answer is yes, and it tells me right here in what I did. Along the way, I made the statement that e to the y, it was equal to x. So I can substitute that here and have dy dx equals 1 over x. So the derivative of the natural log is 1 over x. So if we're updating our chart, we're going to add in, oh geez, sorry, typo here. This x doesn't belong here. The derivative of e to the x is just e to the x. The derivative of a to the x is a to the x times the natural log of a. And the derivative of natural log is 1 over x. Okay. So our next goal is then to mix these in with our other rules. So let's take a look at a couple examples. If we have e to the x times the sine x, here I notice I said times, so we're multiplying. So our e to the x is my function 1, and the sine x is my function 2. So when I set this up for product rule, function 1 is e to the x, and its derivative is e to the x. For function 2, that's my sine x, and the derivative of function 2 is cosine x. So when I put this all together using product rule, I get the first derivative is 1 prime 2, so e to the x times the sine of x, plus 2 prime 1, e to the x times the cosine of x. If you'd like to factor out that e to the x, you can, and you have a sine x plus cosine x left over, and that's my derivative. Number 2, you've got an ln x over a tangent x, so this is a quotient rule. So the top is your natural log of x, and the top prime is 1 over x. The bottom is tangent x, and the derivative is secant squared. Be right there. And then we take the derivative and we put it together using quotient rule. This is top prime bottom, so 1 over x times the tangent of x minus bottom prime top, which is natural log of x secant squared x, all over the bottom, which is tangent, and we're going to square that, so tangent squared x. Now, if I want to get rid of my fractions and fractions, I can multiply everything in the top and everything in the bottom by an x, and that'll give me the tangent of x minus x times the natural log of x times the secant squared x, all over x tangent squared x. And that's my final answer. Again, you don't want to cancel out the tangents because you don't have one in all 3 places. Number 3, again, we've got another product rule here. We're taking the x squared, which is our function 1, times the ln of x, which is our function 2. So function 1 is your x squared. Function 1 prime would be 2x. Your function 2 is ln x, and 2 prime is 1 over x. Put this together using your product rule, and you've got 1 prime 2, which is the 2x ln x, plus x squared times 1 over x. And that's going to simplify. One of those will cancel top and bottom, so that's just x. Again, if you want to factor out the x, you can, but I'm going to leave mine just as it is. And there's problem number 3. Number 4, flashback to sine squared. So this is the same as sine of x, everything squared. So when we take our derivative, we bring down the 2, leave the sine x, new exponent is 1, times its derivative, which is cosine x. So this is just 2 sine x cosine x. Number 5. Now, here's the difference. Notice on this one, the square was above the n, and that meant that all of sine of x was squared. In number 5, notice that the square is on the x, which is in the argument. So the x squared is my inside function, and the sine is my outside function. So when I take the derivative here, f prime of x is equal to, we start with the blue one, the derivative of sine is cosine. Leave the argument alone, and then multiply by the derivative of the inside, which is 2x. Make sure that you understand the difference between this one and the one above it. And that's the end of our lecture.